Imagine you're planning a road trip and need to find where two highways intersect. Or maybe you're trying to figure out when two different phone plans cost the same amount. These real world problems can be solved using a powerful mathematical technique called graphing systems of equations. Welcome to our comprehensive guide on solving systems of equations by graphing. In this video series, we'll master this visual approach to finding solutions that satisfy multiple equations simultaneously. A system of equations is simply a set of two or more equations that share the same variables. For example, we might have two equations both containing the variables x and y. Our goal is to find the values of x and y that make both equations true at the same time. The graphing method gives us a visual way to see exactly where this happens. This intersection point represents the solution to our system. The coordinates of this point are the x and y values that satisfy both equations simultaneously. This is the power of the graphing method. It shows us the solution visually. Throughout this video series, we'll explore the key concepts behind this method, learn step-by-step techniques for graphing equations, and work through detailed examples. We'll also discover when systems have one solution, no solution, or infinitely many solutions. The graphing method is particularly effective for two-dimensional systems with two variables, and it provides excellent visual insight into the nature of solutions. By the end of this series, you'll have the confidence to tackle any system of linear equations using this powerful visual approach. Linear equations are the foundation of graphing systems of equations. Understanding their structure and behavior is crucial for solving these systems effectively. A linear equation, when graphed on a coordinate plane, always forms a perfectly straight line. Every single point on this line represents a solution to that equation. The most useful form for graphing linear equations is called slope-intercept form. This form is written as y equals mx plus b. In this form, the letter m represents the slope of the line. The slope tells us how steep the line is and in which direction it goes. The letter b represents the y-intercept, which is the point where the line crosses the y-axis. The slope, represented by m, measures the steepness of the line. It tells us how much y changes for every unit that x increases. A positive slope means the line goes up from left to right, while a negative slope means it goes down. The slope is calculated as rise over run. In this example, when x increases by 1 unit, y increases by 2 units, giving us a slope of 2 over 1, which equals 2. Now let's look at the y-intercept. This is the value of b in our equation, and it represents exactly where the line crosses the y-axis. In our example, the y-intercept is 1. Let's see how changing the slope affects the line. Watch what happens when we change the slope from 2 to -1, keeping the same y-intercept. Notice how the negative slope creates a line that goes down from left to right. The steeper the slope, the more dramatic the angle. A slope of 0 creates a horizontal line, while an undefined slope creates a vertical line. Now let's see how changing the y-intercept affects the line. We'll keep the slope the same, but change where the line crosses the y-axis. All three lines have the same slope of 1/2, so they're parallel to each other. But they cross the y-axis at different points. 3, 0, and -2. This shows how the y-intercept shifts the entire line up or down. Understanding slope-intercept form makes graphing much easier. You can quickly identify the y-intercept and use the slope to find additional points. This knowledge is essential when we graph systems of equations to find their intersection points. Now that we understand the key concepts, it's time to learn the actual process of graphing linear equations. The first step in solving any system of equations by graphing is to graph each equation on the same coordinate plane. There are three main methods you can use to graph a linear equation. Let me show you each method clearly. The first and most common method uses the slope-intercept form. When your equation is written as y equals mx plus b, you can easily identify the slope m and the y-intercept b. Let me demonstrate this with a concrete example. We'll graph the equation y equals 2x plus 1. In this equation, our slope m equals 2 and our y-intercept b equals 1. This means the line crosses the y-axis at the point 0, 1, and for every 1 unit we move right, we move up 2 units. Step 1, plot the y-intercept. Since b equals 1, we place our first point at coordinates 0, 1 on the y-axis. Step 2, use the slope to find another point. Since our slope is 2, which means 2 over 1, we move right 1 unit and up 2 units from our y-intercept. Starting from 0, 1, I move right 1 unit to x equals 1, then up 2 units to y equals 3. This gives us our second point at coordinates 1, 3. Step 3. Draw a straight line through both points. This line represents all solutions to the equation y equals 2x plus 1. Perfect. We've successfully graphed our first equation. Now let me show you how to graph a second equation on the same coordinate plane. For our system of equations, let's add a second equation, y equals negative x plus 4. In this second equation, the slope m equals negative 1 and the y-intercept b equals 4. This means the line crosses the y-axis at 0, 4, and for every 1 unit right, we move down 1 unit. Following the same process, I first plot the y-intercept at 0, 4. Then I use the slope of negative 1. From 0, 4, I move right 1 unit and down 1 unit to reach 1, 3. Now I draw the line through these 2 points. Notice how this second line has a different slope and intersects our first line at a specific point. Both lines intersect at the point 1, 3. This intersection point is the solution to our system of equations, which we'll explore in detail in the next section. Before we move on, let me quickly mention the other 2 methods for graphing linear equations. You can also graph by finding the x and y intercepts or by creating a table of values. The slope-intercept method we just used is often the most efficient, but all 3 methods will give you the same accurate graph. The key to successful graphing is accuracy and careful plotting of points. Always double-check your y-intercept and use the slope correctly to find additional points. In the next section, we'll learn how to determine the intersection point and identify the solution to the system. Now that we have both equations graphed on the same coordinate plane, we need to analyze how these 2 lines relate to each other. This relationship will tell us exactly what type of solution our system has. There are 3 possible relationships between 2 lines. The first and most common case is when the lines intersect at exactly 1 point. When this happens, our system has exactly 1 solution. To find the solution, we need to locate the exact point where the 2 lines cross. This intersection point represents the x and y values that satisfy both equations simultaneously. Now we need to read the coordinates of this intersection point carefully. We can see that the x-coordinate is approximately 1.33 and the y-coordinate is approximately 1.67. For exact values, this point is at 4/3, 5/3. To verify this solution, we must substitute these x and y values back into both original equations. If both equations are satisfied, then we have found the correct solution to our system. Now let's examine the second possible case, when 2 lines are parallel to each other. When 2 lines are parallel, they have the same slope but different y-intercepts. This means they will never intersect, no matter how far we extend them in either direction. Since parallel lines never intersect, there's no point that satisfies both equations. Therefore, this system has no solution. We call this type of system inconsistent. The third and final case occurs when both equations represent the exact same line. When 2 equations represent the same line, every point on the line is a solution to both equations. This means the system has infinitely many solutions. We call this type of system dependent because one equation depends on the other. They're essentially the same equation written in different forms. Any point you choose on this line will satisfy both original equations. To summarize the process of determining intersections and identifying solutions. First, examine how your 2 graphed lines relate to each other. If they intersect at one point, read the coordinates carefully and verify by substitution. If they're parallel, the system has no solution. If they're the same line, the system has infinitely many solutions. Remember, the key to success is careful observation of the graphed lines and precise reading of coordinates when an intersection exists. Always verify your solution by substituting back into the original equations to ensure accuracy. Now we'll work through our first example to see how graphing helps us solve a system of equations. This example will show you a system that has exactly 1 solution. Here's our system of 2 linear equations. The first equation is y equals x plus 1, and the second equation is y equals negative x plus 3. To solve this system by graphing, we need to plot both equations on the same coordinate plane and find where they intersect. First, I'll set up our coordinate plane with clearly labeled axes. This will help us visualize both equations. Let's start with the first equation, y equals x plus 1. This is in slope-intercept form, where the slope is 1 and the y-intercept is 1. The slope of 1 means the line rises 1 unit up for every 1 unit to the right. The y-intercept of 1 means the line crosses the y-axis at the point 0, 1. Here's the y-intercept at 0, 1. Now I'll use the slope to find another point. Using the slope of 1, I move right 1 unit and up 1 unit from the y-intercept. This gives me the point 1, 2. Now I can draw the complete line for y equals x plus 1. Now for the second equation, y equals negative x plus 3. This has a slope of negative 1 and a y-intercept of 3. The slope of negative 1 means the line falls 1 unit down for every 1 unit to the right. The y-intercept of 3 means it crosses the y-axis at 0, 3. Here's the y-intercept at 0, 3. Using the slope of negative 1, I'll find another point. From 0, 3, I move right 1 unit and down 1 unit. This gives me the point 1, 2. Notice this is the same point we found on the first line. Now I'll draw the complete line for y equals negative x plus 3. The two lines intersect at exactly one point, 1, 2. This intersection point is the solution to our system of equations. Now we need to verify that this point actually satisfies both equations. Let me check this by substituting x equals 1 and y equals 2 into each equation. Let me verify this solution by substituting our values into both original equations. For the first equation, y equals x plus 1, I substitute x equals 1 and y equals 2. This gives me 2 equals 1 plus 1, which simplifies to 2 equals 2. This is true. For the second equation, y equals negative x plus 3, I substitute the same values. This gives me 2 equals negative 1 plus 3, which simplifies to 2 equals 2. This is also true. Since the point 1, 2 satisfies both equations, we can confirm that this is indeed the correct and unique solution to our system. This demonstrates how graphing helps us visualize the solution as the intersection point of two lines. Now we'll examine our second example, which demonstrates a system with no solution. This occurs when we have parallel lines that never intersect. Before we graph these equations, notice something important about their structure. Both equations are in slope-intercept form, y equals mx plus b. Let's analyze each equation carefully. The first equation, y equals 2x plus 1, has a slope of 2 and a y-intercept of 1. The second equation, y equals 2x plus 3, also has a slope of 2, but its y-intercept is 3. Notice that both equations have identical slopes. This is a crucial observation. When two lines have the same slope but different y-intercepts, they are parallel lines. Parallel lines never intersect, which means this system will have no solution. Now let's graph both equations to see this visually. We'll start with the first equation, y equals 2x plus 1. Step 1, we plot the y-intercept. For y equals 2x plus 1, the y-intercept is 1, so we plot the point at coordinates 0, 1. Step 2, we use the slope of 2. Remember, slope equals rise over run. A slope of 2 means we rise 2 units and run 1 unit to the right. Step 3, we draw the line through these points. This gives us the graph of y equals 2x plus 1. Now let's graph the second equation, y equals 2x plus 3, using the same process. For the second equation, the y-intercept is 3, so we plot the point at coordinates 0, 3. The slope is again 2, so we rise 2 units and run 1 unit to the right from our y-intercept. Now we draw the line through these points. This gives us the graph of y equals 2x plus 3. Now we can clearly see what happened. Both lines have been graphed, and they are completely parallel to each other. The lines are parallel, which means they will never intersect, no matter how far we extend them. Since there is no point of intersection, this system has no solution. In mathematical terms, we call this an inconsistent system. Remember this key pattern. When two linear equations have the same slope but different y-intercepts, the system will always have no solution. Now that we've explored solving systems of equations by graphing, it's important to understand the limitations of this method and when to use alternative approaches. The first major limitation of graphing by hand is precision. When solutions involve non-integer coordinates, it becomes very difficult to read exact values from a hand-drawn graph. For example, if we try to estimate this intersection point by hand, we might read it as 1.5, 2.1, but the actual solution is approximately 1.636, 2.191. Hand graphing has several other limitations. It's time-consuming for complex equations, difficult when dealing with large coordinate values, and prone to human error when plotting points. Fortunately, technology provides excellent solutions to these limitations. Graphing calculators offer precise plotting, built-in solve functions, and zoom capabilities for improved accuracy. Graphing software like Desmos and GeoGebra provide even more powerful tools. They offer interactive graphing with exact solutions, easy equation input, and multiple viewing options. While graphing is excellent for visual understanding and learning concepts, algebraic methods like substitution and elimination are preferred when you need exact solutions, are working with complex systems, or require high precision. To recap our method for solving systems of equations by graphing: first, graph each equation on the same coordinate plane. Second, identify where the lines intersect. Third, read the coordinates of the intersection point. Finally, verify your solution by substituting back into both original equations. Remember the three types of solutions you might encounter: one solution when lines intersect at one point, no solution when lines are parallel, and infinite solutions when the lines are identical. The key takeaways from solving systems of equations by graphing are: graphing provides valuable visual insight into the relationships between equations. Technology can significantly improve accuracy and efficiency. Algebraic methods should be used when precision is critical, and you should always verify your solutions. Thanks for watching. If this video helped you understand systems of equations, please like, subscribe, and let me know in the comments what math topics you'd like to see next. Keep practicing, and remember that mathematics is all about understanding the relationships between different concepts.